This is a L'Hopital's rule. It's not lhospitals rule. It's L'Hopital. And so what we're going to be dealing with is an indeterminate form. And so what that means is our limit cannot be determined by its two functions that create it. So if you look at it, we have a rational function here. And so you have a polynomial on the top and a polynomial on the bottom. And even though we can find the limit of each together, they don't give us the limit of the function. That's an indeterminate form. So we have our 1. If we plug it in to the top, we end up getting 0. And if you plug the bottom in, you get 0. So we have an undetermined limit here. So we already knew our rule from before. When we see 0 over 0, we knew something canceled. So we take the limit as it approaches 1, and we factor it. And we simplify. Now we have the limit of the top, which would be 1, and the limit of the bottom, which is 1 plus 1, and we end up with 1/2. So that was the one method. This is a new one. So with L'Hopital's rule, if we have an indeterminate form of these two types, which is 0 over 0, or an infinity over an infinity, then our limit is actually the same as the limit of the derivatives of the top and the bottom. So we can take the derivative of the top and the derivative of the bottom, and it'll actually be the limit of our function as well. So it works like this. We're going to keep the 1. Now if we take the derivative of the top, we end up with 2x minus 1. Derivative of the bottom is 2x. And so now we can say the limit, oops, I don't need the limit anymore. Now we can plug the 1 in, and we get 2 times 1 minus 1. 2 times 1, and you can see that this becomes 1/2. Same exact answer. So this is still the better method. It's the much more novel method. So we should really stick with that one. But L'Hopital does work as long as it has these two indeterminate forms. So let's try another one. So on this one, we can't actually cancel. Factoring, that's going to be way too complicated. You could do it, and you could factor this one using the difference of cubes and then the difference of squares up here, but we're going to go straight for L'Hopital's. So first we want to make sure that it has the correct indeterminate form. It needs to be 0 over 0 or infinity over infinity. If it's not, then we're not going to be using L'Hopital's rule. So this would become the limit. Oops, we got to check it. I just talked about that. So if we plug in 1, we get 1 to the 8th minus 1, which is 0. And we get 1 cubed minus 1, which is 0. So check and check. So now we can apply L'Hopital's rule. So this would be 8x to the 7th. And this would be 3x squared. And then we rewrite it. Limit as x approaches 1. And this is 8/3. X to the 5th, which would be 8/3. So it's a 5. And that's 8/3. Now we always want to check this with our calculator, so let's pull it up and take a look. All right, so we plug in our calculator and we have two options. We go graph, trace, and 1, and obviously doesn't work. But if you scroll to the left and you scroll to the right of 1, it approaches it. Not as nice, right? So you can see it's around 8/3, but if we go to our table set, plug in 1, and we get really, really, really close to that 1, like this. See, really, really close. Then we can actually see what it's approaching, and you can see that's 8/3, 2.6667. All right, let's try another one. So if we plug in infinity here, that would become infinity and infinity. So we're going to be getting infinity over infinity. So again, indeterminate form that we can use. That's one of them. And so now we take the derivative. But before that, first we want to always rewrite those logarithms, right? So that's 1/2 natural log of x, x squared. Remember, this is x to the 1/2. We put an ln in front of it, and that half goes in front. Now we can take the derivative. So this is 1/2 times 1 over x, and that's 2x. I made a huge mistake because I forgot to write limit. Limit as x approaches infinity. That would be 1/2 times 1 over x, 2x. And then we rewrite, basically simplifying. So the 2 and the x both go to the denominator because they're both denominators. So that would be 4x squared. Now, the limit as we approach infinity of this is just 0. That's just our rational expressions. So there we have it. So we're just rewriting it, making sure it meets our condition for the indeterminate form. It needs to be 0 over 0 or infinity over infinity, and we're good. And if it is, we can take the derivative. So we took the derivative of the top, derivative of the bottom. You have to do both, simplify, and then check it. And then now we'll plug it in the calculator. So we plug it in our calculator. We look at our window, and we're supposed to be getting 0. So I'm going to put in a big number here. Put in a big number down here for my change so that I'm approaching infinity. And you can see it's getting smaller and smaller and smaller and smaller. So it's approaching 0. So that checks. All right, let's do one more. So if I plug 0 into here, hyperbolic sine would be 0 minus 0 and 0. So we're going to get 0 over 0. That's a good form. Now we can take the derivative. So hyperbolic sine would be cosine, and that's minus 1, and we get 3x squared. And then now we plug it in, we're done, right? Well, let's see. If I plug in 0, that would become 1 minus 1, which is 0 over 0. Well, that's still indeterminate. So what do? Well, it meets the condition. So guess what you can do? Exactly, you do it again. So this would become hyperbolic sine of x over 6x, and then we check it, and that's 0 over 0. Okay, this is getting ridiculous. But the reason it's here is so that you can do this. Okay, so that would now become the limit as x approaches 0 of hyperbolic cosine of x over 6. And then now if we plug in 0, we get the hyperbolic cosine of 0 over 6, which is 1 over 6. And there you have it. So 1/6 is that. Plugging it in the calculator, getting my table set really close, so we're approaching 0. So I have 0 here. And then I have my change in table very, very close. Second table. There you go. Same value. So you can kind of think of this like a little magic wand. If we have this indeterminate form of these two, you wave the wand and it becomes a lot simpler. So it's a good method.